In this video, we're going to look at an application of improper integrals. One of the questions that frequently comes up with improper integrals is when would we ever use this? And I would argue that both biology, mathematical biology, and physics use this kind of integral all the time. Anytime they extend a field, a strength, here we're going to be looking at distances out towards infinity, frequently an integral is involved, and that naturally means that we're dealing with an improper integral. What we're going to look at here is the Universal Law of Gravitation. So this is the gravitation force between any two objects of different masses and at different distances or particular distance apart. And we see in that rule the inverse square law, where if two objects are r meters apart or kilometers apart, as we double the distance, we cut the force between them by 4. We're going to look at the case where we have mass 2 being the Earth, and mass 1 is some object that we're lifting off of the Earth. Now, when we're taking something off the Earth and moving it away, what's happening is we're changing r. When we move far enough away from the surface of the Earth, we can't use our simple 9.8 meters per second squared acceleration. We actually have to go back to Newton's Universal Law of Gravitation. But what we can do is talk about distances on this order of magnitude, and then talk about distances that are getting larger and larger. Let's turn this example to something a little more focused, where we have, again, the surface of the Earth, and then not to scale at all, but we move that object up. Again, here, we're imagining something moving up in an elevator. If we have the distance that we're moving by, then we can get the amount of work done as the gravitational force times the distance. And that's straightforward because when we make the distance small, then F is approximately constant. However, if we're trying to lift something like a satellite up into orbit, then this d is large. And d large is not a fundamental problem. The problem is that it leads to F is changing as we move that object. And so we can't just take F times distance because F is not a constant value. The force it takes to lift something off the surface is lower than the force it takes to lift off the surface of the Earth is smaller than the force it takes to lift the same distance once it's already off the surface of the Earth and further away. That comes back to this r value here. Well, how do we get around that? We use an integral. We would integrate the force times a little unit of distance, or delta r, and that would let us accumulate the amount of work done as we move up little piece by little piece through this scenario. Let's make this more concrete. We're going to write down the integral that represents the work required to move a mass of m1 kilograms, so think of an object, a satellite, a person, from the surface of the Earth to a point completely out of the reach of Earth's gravity. And of course, that is where we get our infinity from here. To be out of the reach of Earth's gravity is actually impossible. It just gets smaller and smaller and smaller. So we capture that idea by letting the distance approach infinity. And so the work we're talking about here is an integral of force times little units of r, and the initial distance between the 2 points is exactly what the distance is from the center of the Earth to the surface of the Earth, center to the surface. And then we imagine moving up little units of delta r or little units of dr as we move upwards. And we do that all the way out to infinity. And so that's what we capture with this notation here. We actually have formulas, though, for our force. It's g m1 m2 over r squared dr. That's the force from Newton's Universal Law of Gravitation. And we can see here how that natural statement of find the work required or the energy required to move something out of the reach of Earth's gravity naturally leads to an improper integral. We're now in a position to actually evaluate this integral. Notice there are a whole pile of constants. In fact, all of 3 of these variables here are constants. So what we're going to do is a 2-stage process, in one step though. The first thing we're going to do is apply our definition. Because we have an improper integral, we are going to integrate to some other upper value b and let that b value approach infinity. That handles the infinite boundary there. We also have r naught, that's fine. We're actually going to slide this over a hair though. And we're also going to bring out front the g, m1, and m2. And that leaves r to the -2 as part of our integral. So the actual integration step is going to be straightforward if we just leave the constants out front. All right, we then keep the limit here. We'll evaluate that last. We keep the constants where they are, and we do the integration step. We have r to the -2, add 1 to the power, divide by the new power, evaluate that between b and r naught, copy the limit, copy the gm1, m2s, and we'll have -1 times 1 over b. That's what the r to the -1 with b subbed in. Let's be careful here that we're subbing in r values. That was our variable of integration. And the next one is 1 over r naught. Perfect. Now we're going to let our b value get larger and larger. So this corresponds to the energy to lift from r naught to some fixed point b above the surface of the Earth. And now we're letting that fixed point above the surface become infinitely large. As we do that, we scan across and see this is the only b value. It's in the denominator. So if b is getting larger and larger, that term is going to 0 and goes away. And at the end of the day, we have a double negative. And so what plays a role in our work calculation is simply the gravitational constant, the size of the two masses, and how far we were originally from the center of the Earth, the initial r naught. That's all that plays a role if we're going to lift some object from the surface of the Earth out towards infinity. What we can do now is assess this in a particular context. We're going to imagine mass 2 is the mass of the Earth, 10 to the 24 kilograms roughly, and let's imagine the work it takes to lift one person up there. So the energy or work we're talking about here was based on that integral from r naught, so 6.38 times 10 to the 6 meters. That's the radius of the Earth, all the way up to infinity. And the gm1, m2 we'll leave in their form right now. We did this work on the last page. That gave us gm1, m2 times 1 over r naught, or that million kilometers. And then we can sub in our values. If we sub in those values, separating our g's from our 6's a little bit more clearly here, then we plug in g, we plug in m1, our 70 kilograms, our m2, and we can see we've got an interesting variety of exponents here for the powers of 10. If we do that calculation though, we end up with something around 4.4 times 10 to the 9 joules. That is the work or the energy required to take a person from the surface of the Earth all the way out towards infinity. That is the amount of energy it would take to remove a person from the surface of the Earth outside of Earth's gravitational well. That can feel a little cold and analytic though. What we're going to look at next is a little conversion to velocities and talking about escape velocities. So again, if we had something at the surface of the Earth and we're trying to move it out towards the infinite point or all the way away from Earth's gravitational well, one of the things that we might want to consider is how quickly would we have to be moving? In other words, if we had a really fast car, a really fast plane, could it drive fast enough to have the same amount of energy? So if we equate our kinetic energy equal to the work required, or the energy required, to escape the field, escape the Earth, we can set those equal, and we can actually solve for the speed we'd have to be going. 1/2 mv squared equals the g m1 m2 times 1 over r naught. That was our result of our integral here, and the mass we're talking about is the mass of the thing we're lifting. We called that m1 before. And so we actually get a nice expression here. The speed that we need to go would be given by g m2 times 2, and that'd be v squared, 1 over r naught. And that gives us v is the square root of 2 universal gravitation constant, mass of the Earth, radius of the Earth. And if we plug in the values we have, we actually end up with a value of approximately 11,200. Now, what are the units of that? All the units we've been working with are standard SI units, meters, joules, newtons, and so on. So this would be in meters per second, or 11.2 kilometers per second. And we see very quickly now why we don't achieve escape velocity at the surface of the Earth with the kind of rocket technology we use. We have to thrust or add more energy in as the object is flying away, because we can't achieve these kinds of speeds with the kind of vehicles that we have currently on Earth. So if we did want to, though, if we ever wanted to, say on a surface of a planet without any air, so there's no air resistance, if we wanted to escape one like the Earth, we would have to be going 11 kilometers per second to be able to use that energy and convert it into potential energy and have that object escape the gravitational field.